Have you ever looked up at the night sky and wondered, where do all these twinkling stars come from? Our universe is a grand cosmic nursery where stars are born from massive swirling clouds of gas and dust. Picture this, an immense cloud in the vast expanse of space filled with hydrogen and helium, the most basic elements in the universe. Gravity, the great sculptor of the cosmos, pulls these particles together, creating a dense, hot core. This is the birth of a protostar, the infant stage of a star's life. As the protostar continues to collect more and more material, it grows, and the pressure and temperature at its core rise dramatically. When the heat and pressure reach a critical point, nuclear fusion begins, and the protostar graduates into a full-fledged star, a main sequence star, to be precise. So, the stars we see twinkling in the night sky all started their journey in a cloud of gas and dust. That we know where stars come from, what happens to them over their lifetime? Every star, however grand or modest, embarks on a journey that is both fascinating and intricate. This celestial journey, known as the star's life cycle, is a process that can span billions of years. Stars, similar to our own sun, go through a series of stages starting from the main sequence phase, evolving into a red giant, and finally, ending as a white dwarf. The main sequence phase is where the magic begins. It's the longest stage in a star's life, lasting for about 90% of its existence. During this phase, stars are in a state of equilibrium, with the inward pull of gravity perfectly balanced by the outward push of pressure from nuclear fusion at the core. From this stable state, stars eventually evolve into red giants. This is when things start to get a bit dramatic. The star's core contracts as it runs low on hydrogen fuel, and the outer layers expand. The star grows in size, becoming hundreds or even thousands of times larger than it was during the main sequence phase. The outer layers also cool down, giving the star a reddish appearance, hence the name, red giant. Finally, the star enters the white dwarf stage. The outer layers of the star are shed into space, creating a beautiful cloud of gas and dust, known as a planetary nebula. All that remains is the hot, dense core of the star, which cools and dims over time. This is the white dwarf, a faint echo of the star's once vibrant existence. It's important to note that not all stars follow this exact path. The fate of a star is largely determined by its mass. Larger stars, for instance, end their lives in a much more spectacular fashion, as supernovae. But that's a story for another time. From birth to maturity, stars undergo a transformation that can take billions of years. This journey, while long and complex, is a testament to the dynamic and ever-evolving nature of our universe. But what keeps these stars shining for so long, you might wonder? The answer lies in an incredible process known as nuclear fusion. Within the fiery heart of a star, intense pressure and heat force hydrogen atoms to combine, forming helium. This isn't just a simple change of state, though. The magic of nuclear fusion is that it doesn't just rearrange atoms, it transforms them. This transformation isn't without a show. In the process, a staggering amount of energy is released, illuminating the star and allowing it to shine brightly in the dark expanse of space. Imagine the energy produced by countless atomic bombs going off every second, and you'll start to grasp the enormous power produced by nuclear fusion. So the next time you gaze up at the night sky and marvel at the twinkling stars, remember, it's all thanks to nuclear fusion. This incredible process is, without a doubt, the engine that powers stars and keeps them shining brightly. What happens when a star runs out of fuel? It's a question that sparks curiosity and wonder. You see, stars are not perpetual machines. They have a life cycle, and like all things in existence, they reach a point where they can no longer sustain their vibrant glow. At the heart of a star, a process called nuclear fusion fuels its existence, converting hydrogen into helium and releasing a tremendous amount of energy. This energy is what makes a star shine so brilliantly. However, the hydrogen fuel in a star is finite. When a star exhausts its hydrogen reserves, the nuclear fusion process slows down and eventually ceases. This marks a significant turning point in a star's life cycle. The star begins to contract under its own weight, and its core becomes increasingly dense. The outer layers expand and the star cools and reddens, morphing into what we call a red giant. When a star depletes its fuel, it undergoes a dramatic shift, setting the stage for its final act. What happens when a massive star collapses under its own weight? Imagine this. A star, once radiant and full of energy, has exhausted its nuclear fuel. It starts to shrink, surrendering to the relentless pull of its own gravity. But this isn't a quiet, gentle fade into the cosmic night. No, the star's demise is anything but silent. This is where the grand spectacle of a supernova enters the scene. A supernova is an astronomical event of epic proportions. It's the final dramatic act of a massive star's life, a celestial display that outshines entire galaxies, even if only for a brief moment. You see, as the star collapses under its own weight, the core becomes so dense and hot that it triggers a shockwave. This shockwave races outward, ripping through the layers of the star with incredible force. The star, once a beacon of light and heat, suddenly explodes, releasing a staggering amount of energy into the cosmos. To put it into perspective, this explosion is so powerful that it can briefly outshine the star's entire home galaxy. That's billions of stars outshone by a single dying star. A supernova can radiate as much energy in a few weeks as our sun will in its entire 10 billion-year lifetime. But a supernova is more than just a spectacular light show, it's also a cosmic forge. The explosion triggers nuclear reactions that create new elements heavier than iron. These elements, flung into space by the supernova blast, become the raw materials for new stars, new planets, and perhaps even life. In a way, we owe our existence to these celestial fireworks. The iron in our blood, the calcium in our bones, the oxygen we breathe, they were all forged in the heart of a dying star, scattered across the cosmos by a supernova explosion. In a final dramatic display, a massive star ends its life in a brilliant supernova explosion. Even in death, stars continue to shape the universe, their explosive endings seeding the cosmos with the building blocks of new stars, planets, and life. What remains after a supernova explosion? This is a question that has intrigued astronomers and space enthusiasts alike for centuries. When a massive star, much larger than our own sun, exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. This magnificent display of cosmic fireworks marks the end of the star's life cycle. But it's not the end of the story, far from it. What remains after this cosmic spectacle is just as fascinating. Depending on the star's initial mass, two main outcomes are possible: a neutron star or a black hole. Let's start with neutron stars. They are the densest known objects in the universe. Imagine squeezing a mass about 1.4 times that of our sun into a sphere with a diameter of just about 20 kilometers. That's a neutron star for you. These stars are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. Their intense gravity and rapid rotation create extreme conditions, producing some of the most powerful electromagnetic fields in the universe. On the other hand, if the original star was considerably larger, say, about 3 times the mass of our sun or more, the story unfolds differently. The gravitational collapse continues unimpeded, and a black hole is born. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They are invisible to our eyes, but their presence can be inferred by their gravitational effects on surrounding matter. These outcomes of a star's demise, neutron stars and black holes, are some of the most intriguing and mysterious objects in the universe. They challenge our understanding of physics, test the limits of our imagination, and remind us of the incredible complexity and beauty of the cosmos. The death of a star can give birth to some of the most mysterious and fascinating phenomena in the universe. So, what does the life and death of a star mean for the cosmos? The impact of these celestial events is far-reaching and profoundly transformative. You see, stars are the architects of the cosmos. Their birth, life, and death processes sculpt and shape the universe in numerous ways. The material expelled by dying stars, including heavy elements like iron, gold, and uranium, spreads across the cosmos. These elements, forged within the heart of stars, enrich the interstellar medium, the space between stars. This stardust serves as the raw material for the birth of new stars, planets, and even life itself. Moreover, the cataclysmic events such as supernova explosions and the subsequent formation of neutron stars or black holes significantly influence the surrounding space. They warp the fabric of space-time and can trigger the birth of new stars by compressing nearby gas and dust clouds. In their life and death, stars play a pivotal role in shaping the universe as we know it.